Welcome back to lecture 2 of business calculus. Okay. In this first part, which is going to be sort of following just like the last one, shorter first part, longer second part. Hopefully, in the coming weeks, they will sort of average out, and we won't have the big discrepancy in length. But today, in all likelihood, shorter first part, longer second part. But anyway, let's jump right in. So our first topic today is the algebra of functions, right? So we have these functions, right, that map one set to another. And the question is, how can we combine them in order to get new functions, right? And then how does that affect the domain of our functions, right? We have this notion of like algebra in the real numbers, right? The number 5 plus the number 3 gives us the number 8. Could we have like the function f plus the function g give us a new function, right? And everything works exactly how you'd expect it there, right? So we can combine functions in the ways you would expect. Okay, so in order to do this, we'll say f and g are functions of the real numbers, right? And we'll say that they have domains a and b respectively, right? So how can we combine these, right? Well, as I said, they combine the natural ways, right? So I guess we'll need a then here. Okay. We can add the functions, right? And when we add the functions, well, we add the outputs, right? And a thing that I want to draw your attention to here is that there's two sorts of addition happening here, right? This is an addition of two functions, right? And the addition of two functions is defined by adding their outputs, right? So then the natural question then is what happens to the domain, right? Well, in order to have this function exist, we need both f and g to exist, right? So our domain is the intersection, right? Where this intersection happens or, works as you would expect, again, as covered in 118. But our intersection is all the stuff that's in both, right? Just like addition, we can subtract, and it works like you'd expect, right? F minus g of x, well, you can find that by subtracting f of x minus g of x. We can multiply, okay, f times g of x, and once again, you can calculate f times g of x by multiplying together f of x and g of x. And then our last one for good measure, what about f over g of x? Well, that's nothing but f of x over g of x. Okay. Our domain tells a similar story for our first three, but our domain on this last one is a little bit more complicated, right? We do need this a intersect b, but we also need to worry about division by 0 here, right? So our domain is, well, everywhere that both of those things hold, right? It's all of our x's. It's all of our x's, where x's in a intersect b, and g of x does not equal 0. Okay, so let's do a few examples of this, right? Let's say we'll say f of x is 1 over x minus 1, g of x, we'll say it's 2 times the square root of x, okay? And we want to find the functions, we'll say f plus g of x, f minus g of x, f times g of x, f over g of x, and state their domains. So starting with f plus g of x, right? We're going to have f of x plus g of x. Nice and simple. F minus g of x, well, that's f of x minus g of x, right? The product of our functions, right? Well, that's simply the product of the functions. Going to be f times g, right? So we're going to have 2 over root x over x minus 1. And our last one, f over g of x. Well, that's going to be, well, we're going to get f, so 1 over x minus 1 over 2 root x. We have a denominator in our numerator, so it can get moved down here. And we're going to get 1 over 2 root x times x minus 1. Okay. Now our next obvious question would be to look at their domains. Okay. And in order to do that, remember we take their intersections, and then we need a little bit of an extra case considered for the last one. So we'll call A is the domain of F. And what's the domain of F? Well, this looks like it's defined everywhere except for when we're dividing by 0, right? So this is everywhere except 1, okay? And what about B? Well, we're taking this square root here, right? And so that means that the input to that square root cannot be negative, right? So B is everywhere greater than or equal to 0, okay? So for these guys, what's our domain, right? Well, it's everywhere that both of these conditions hold, okay? So that would mean that we would need what? Well, we're going to probably have to write this as a set because it's a little bit more complicated. Well, since we're intersecting, we just need them both, right? So we have x is greater than or equal to 0. This comma can, be our and, or you can just write the and x does not equal 1. Okay. So now what's happening here? Okay. Well, we have a product of things, which is good, right? Because of the zero product property. Two things multiplying to be 0 only happens when one is 0 or the other is 0. And this function is going to run into issues when our denominator is 0 and when this square root, when the input is negative, okay? And so when is this denominator equal to 0? Well, it's when x is equal to 1, which we covered here, and it's when x equals 0, right? So for this last one, we have nearly the same thing, our set of all x's, except x has to be strictly greater than 0 here, because if it equals 0, then g of x equals 0, and we're outside of our domain because we're dividing by 0, okay? And so this process, right, this addition, subtraction, multiplication of functions, this allows us to create all of your favorite polynomials, right? Say p of x is x cubed plus 5x squared plus yada, yada, yada. Because we can picture that as the sum and product of a bunch of really, really simple functions. You could even have break down all of your x's or your x cubed in that into a product of say just h of x equals x and multiply it by itself a number of times. So we can build all of our polynomials like that. But here's the next question, right? How do we build something like h of x is the square root of x squared minus 1, right? This is a little bit more complicated. We can't necessarily, with the tools that we've created, build this out of simpler functions, okay? But think about how you would actually go evaluating this, right? If you were to evaluate it, well, first you would probably calculate x squared minus 1, then you would take square roots, right? So h of x is actually sort of two functions, right? First we do something like, g of x is x squared minus 1. Then f of x is the square root of x, okay? And so then using the notation from previously, right? Well, then h of x, well, it would be something like we're feeding our result of g of x into f of x, okay? And this is something known as function composition, okay? And function composition is hugely important because it allows us to build all sorts of new machinery, okay? And you can sort of, picture this a number of different ways, right? When we're talking about function composition, if we want to, write it in sort of these terms, right, of something happening in function land, not in real number land, right? We write something like this: f circle g of x, and that means you do g and then you do f, right? And if you're looking for a picture, okay, we can get direct analogs from, sort of both of our pictures from before, right? If you prefer looking at the amoebas, right, you're going to need 3, right? If you have some function g going like that, and then some function f going like that, well, you can go straight from the red set to the yellowish orange set with f circle g, right? Because first you do g, then you do f, right? If you're partial to the machine diagrams, you can look at it something like this, right? You can look at it a little something like this. We need our two machines. This one would be G, this one would be F, right? And that's a thing you kind of have to be a little bit careful of, right? So what you're doing is first you're doing G, and then you're immediately feeding your result into F, right? And then I guess you would call this whole machine, right? This whole thing would be F circle G, right? Because you're doing G and then F, your initial input comes in here and your output goes out right there, okay? So as before, the next obvious question is, what happens to our domain, okay? Well, we could theoretically run into a problem where G maps, F can't necessarily, take that in. Like in this situation, right? G of x here, G of x can return a negative output, right? Take x equals 0. It's going to give you negative 1. F can't accept that, right? F does not talk well or talk at all with negative inputs. Okay, so our domain, it's this. It's all the x's in the domain of G such that G of x is in the domain of y. Or sorry, the domain of f. Okay, and I know that that's a little bit wordy, but oftentimes these sorts of things, they are more obvious in context, and they don't quite have, the simpler thing of, our previous case, right, where we could just, hey, take your two domains, find the intersection. Okay. We'll do a quick example of these. Okay, so let's say we have f of x is our square root of x, and g of x equals the square root of 2 minus x. Okay, so we want to find and state the domain of the following. Okay, so the first one, let's go just f circle g of x, right? Well, it's going to be f of g of x, right? Okay, well, the square root of the square root is just the fourth root, so it's the fourth root of 2 minus x, okay? And what's our domain here, right? Rather than sort of thinking about this, the other way that we can just do this is to look for the domain of this new function. Well, we have an even root, so the input needs to be positive. Well, that would quickly point it to my domain. X has to be less than or equal to 2, right? Nice and simple. What about the other way, right? What about g of f, right? G circle f, right? Well, we're going to do g, and then everywhere we see an x in g, we'll put an f of x. So 2 minus this, so we get the square root of 2 minus the square root of x. And one thing to notice here is that f of g and g of f are different, right? Here we have something that isn't, commutative like we're used to most of our operations being. Okay, so what's the domain of this? Well, we sort of have two cases. Our square root of x, this guy here, that tells us that x has to be greater than or equal to 0. But then this guy here also tells us that 2 minus the square root of x has to be greater than or equal to 0, right? If you rearrange this, you're going to get that the square root of x has to be less than or equal to 2, or taking squares, x is less than or equal to 4, okay? We need both of these cases to hold, which means we're going to take their intersection. So our domain becomes everything between 0 and 4, inclusive. Next, we'll take a look at f of f, right? So f circle f of x. Well, that's the square root of the square root of x, which is the fourth root of x, and our domain is an immediate x is greater than or equal to 0. Finally, we'll take a look at g circle g of x. All right. We start writing g of x, and then everywhere we see an x, we write g of x. Okay. For the domain of this guy, I'm going to have you do that at home. Okay. Math is not a spectator sport, right? You kind of, at a certain point, just got to jump in and start doing it. I think that if you look back at sort of what we did across these two, you should be able to puzzle out how to find the domain of this guy. So now that we've developed function composition and the algebra of functions and all of that, we sort of have the majority of the building blocks for the models that we're going to see, right? Both in terms of like all of the equations that I'm going to be throwing at you this quarter. We've seen the majority of those. Exponentials will come up in a couple weeks, but calculus handles those really, really well. There's these two main building blocks of actual real world models, though, right? And those are polynomials and rationals, right? So a polynomial, a little refresher from 118, right? They're things that look like p of x is a sub n, x to the n, maybe a sub n minus 1, x to the n minus 1. Then it goes all the way down to, say, a1 x1 plus a0, right? Where we say a sub n does not equal 0, and all of my a sub I are real numbers, okay? So these polynomials are tremendously important for us, okay? And then every once in a while, you'll see real world models that are built of rational functions, right? Which are found by just dividing two polynomials. And so the question is often, well, like, why do these matter? Okay, and here's the answer. Most of the time, in the real world, when we encounter data that we want to understand, that data comes as a series of discrete points, right? We often don't, or we rather almost never actually get, some smooth curve like this. What we do get, though, is a series of these sort of discrete points, right, for when we actually captured our data. And a thing that we're really, really good at, a thing that mathematicians and computer scientists and all of this have worked really hard to do, is find efficient ways to take models like this and find polynomials that sort of do a like best fit of the line, right? You could say take this line, right? That's pretty good. If you wanted something a little bit more complicated, right, you could also view this as a very shallow quadratic, right? That's sort of slowly ramping itself up. And it turns out that whenever you go and draw a line on a piece of paper, right, turns out that whenever you draw the graph of some function, right, say that's what we really like. The moment you draw a graph like this, it turns out that you can always find a polynomial that fits within the stroke of your pen. Okay, so that's sort of why we care. More concretely, something like your supply and demand curves, right? All of the data you get from those is going to be in discrete points, right? But more often than not, they can be approximated very, very well with just a quadratic, right? And so it's those tools that sort of begs the question, like, okay, well, if that's the case, we should spend some time studying them.